Hey everybody, so starting chapter 16 today, which is working with vector fields and understanding their properties using the tools of calculus. So you can think of a vector field as taking an input space and then applying a vector to each point in the space. So if it's in the plane, think of each point being assigned a vector. Obviously, this would be infinitely flooded, so we usually visualize these things with more simplified graphs, which I'll show you. Um, but you can also just think of like the airflow. If you were to have like a diagram of the airflow of the room you're in, this is a vector field because what you'd be able to do is track, let's say, the velocity direction of each particle in a snapshot of the space, and you'd get a feel for what the field of the airflow is in the room. So this is really what a vector field is. So at each point, whether it be in the plane or three space or an n-dimensional space, we assign a vector to it. So we're going to input the coordinates essentially and then assign that a vector. So in doing so, we get some cool extensions of the ideas that we've already played with in calculus. So we're going to look at, what does it look like to differentiate functions in this space? What does it look like to integrate functions in the space? And what does the fundamental theorem of calculus look like in spaces like this? And that's where it becomes really, really interesting. So we're going to start off in 16.1 just looking at the definition of vector fields and what are called gradient fields, and then the notion of a conservative vector field, which you might have heard from in a physics course. Not important if you haven't. And then we're going to peek into 16.5, these two properties of vector fields that I really want us to be acquainted with as we start this chapter, which is the curl and divergence. And they're named pretty well in what they describe about a vector field. You can think how much a vector field is swirling, with a more sophisticated notion than just that. And then divergence, how much is a vector field have this kind of outflow from a certain point of reference. So we'll get into that momentarily. So first, let's get into some definitions and some examples and graphs of what vector fields are. Okay, so a vector field is a function, and we have like a vector notation on it that assigns at each point in some domain D, some plane region for R2, to a two-dimensional vector, and we give it big F of xy. Okay, so it takes a point, and at that point, it gives it a vector, or assigns it a vector. So you can think about at each point in a plane, again, assigning or drawing a vector that has its base at that point and then its length and direction pointing off. Obviously, this would be impossible to do if we this at every single point. But what we do is we kind of choose a certain subset to be representative of the field. Okay, and as long as it's not too crazy, it does a good job of snapshotting what that, what the airflow in the room would look like, etc. So how this would look notationally be something like this. We've got big F of xy is equal to some function of xy I hat plus some function of xy j hat. Or you could think of it in this component form. Another way you could write it a little bit more shorthand is that big F is p I hat plus q j hat, right? Where we know that f, p, and q are functions of x and y. And obviously when we scale up the dimensions, we want these to be, all three-dimensional where they take in x, y, and z, or n-dimensional. So, this, or in R3, we can scale this up and say p plus q, which is a function of x, y, and z, j hat, plus r, which is a function of x, y, z, k hat. So again, you can think of at each point x, y, z in space, and I'm going to quickly move over to a visual aid. That's not my hand drawing, but at each point in R3, assigning some vector that's given to me by p, q, and r, the components which depend on the coordinates of that point in space. So hopefully that makes sense. And again, think of this as being like fluid flow or airflow. So just a quick Google search of what these things look like gives you a pretty good representation. So here we've got some vector fields in R2, as well as some vector fields that are in R3. So given a point x, y, z, assigning it a three-dimensional vector, so it has its own components, its own direction and magnitude. So, and again, even though these are happening at infinitely many points, we typically just get a snapshot or a sample set of points. And again, thinking of fluids, really helpful here. So for a quick example, driving from the notation and see what this might look like in the plane. So we get a two-dimensional vector space, or vector field rather, and this assigns to the I coordinate or component a negative y, and to its j component x squared, given a point x, y in space. So let's take a few sample points. We know the origin is going to get mapped to 0i plus 0j, so this is just the 0 vector, right? Maybe if we look at on the x-axis the point 2, comma 1, so x is 2, y is 1, so we get negative I plus 4j. Maybe we'll look at a point on the y-axis. Let's look at 0, 3. This will give us negative 3 I plus 0j. And let's look at a point on the x-axis to the left. We'll say negative 2, comma 0. This will give us 0i plus 4j. And so maybe we'll start sketching some of these out so we can see what we're talking about. And obviously this isn't systematic. I'm picking random points. At 0, we have the 0 vector, so that's nothing. At 2, comma 1, so at this point, we have the vector negative I 4j. So that's left 1, up 4. So we have this vector drawn in here at 2, 1. At 0, 3, we've got negative 3 I 0j. So at 0, 3, 1, 2, 3, the vector's pointing 3 to the left and 0 down. At negative 2, 0, negative 2, 0, I'm at 0i plus 4j. So nothing in the x direction, positive 4 in the y direction. So something like this. So obviously with a few more points, we could get a better sense of what's happening. But you got to think, if I'm a particle here, this is the force acting on me here. If I'm a particle here, this is the force acting on me here. So if I move to CalcPlot 3D and I throw this in here, a two-dimensional vector field, you'll see that there's an option to scale these vectors. So they're not as long as I drew, because if these things have any meaningful or any substantial magnitude, they're going to quickly flood up the whole plane. So you can scale down your vectors. It's a good idea to do so that you get a better comparative sense of the flow of this thing. You can restrict it to 2D or view it in the 3D. You could set it to use fixed length. Let's say we just care about direction and not the magnitude. And then we don't want that real quick. So, and then you can change the number of vectors, etc. But here you can get a sense of what's happening. So imagine if you're a particle or a floating, little canoe in this pond of water, in this 2D pond of water, what would eventually happen to you? What path would you take based on where you are? That's kind of how to view this. But at each point, x, y, you're being assigned a vector. That's what comprises a vector field. So a example that we all know from a felt sense is the gravitational vector field that's acting on you in any given position. And if you want to see the derivation for this, you can take a look at page 1111. But essentially, the force acting on the object at a given position vector xyz is defined by this. Again, it's the proportional to the two masses, right? So given xyz, you can construct a field that's telling you the force, the magnitude and direction of the force acting on you based on where you are. And, what do we know about gravity? Well, it's stronger the closer you are, right? The smaller the distance, the stronger the force. So when we graph this or visualize this, what do we see? So what we see here is a visualization of this. Again, I just threw some random values in for the parameters, but you can see that it bears the same relationship, whereas we get closer, that distance is getting smaller and smaller, so the magnitude of the denominator is getting smaller and smaller, which means the whole thing is getting larger and larger. So the magnitude of the vectors getting longer and longer, the force is stronger as the closer you get to the center of the Earth. Okay, so the closer you bring two objects together, the more force is applied between them gravitationally. But what's cool is that we can get this visualization and then from a given point in space, find out what that acting force is. So that's what the vector field gives us as a function. So here I just have it written out, and again, these are just the same expression here quoted in, but we sub out the x, y, and z parts there for the components. So again, I'll leave those in the notes so you can play with those vector fields in CalcPlot. The last notion I want to get to is that of a gradient field and a conservative vector field, and then we'll move into curl and divergence, so these two properties of vector fields. So first off, let's look at gradient fields. So for a gradient field, if we're given a function, a scalar function f of x, y, then we remember that gradient of f gives the partial of x as the I component, the partial with respect to x as the I component, and the partial with respect to y as the j component. So the x and y components is the partial of the function with respect to those variables, right? And it's the direction of maximal change for the scalar function f, right? So it tells you where to point yourself for maximal change in the z. And then if we scale it up a dimension, we know that this goes to, for some f of x, y, z, so it's a scalar function with 3 input variables, then the gradient field is the partial with respect to xi, partial yj, partial zk. Again, what is this doing? This is assigning to each point xy or xyz, it's giving it a vector, right? So this is a vector field, and it's what we call a gradient field. So I'm going to show you an example here and see how this relates to what we already know about gradients and vector fields. So if we take this one, excuse me, minus y cubed, and we want to find the gradient vector field and then plot it. Well, then what we're going to need is the partial with respect to x and the partial with respect to y. So partial with respect to x here is 2xy. Partial with respect to y is x squared minus 3y squared. So then the gradient vector field is the vector valued function that, or the vector field function, sorry, that gives you this. 2xy for your I component plus x squared minus 3y squared for your j component. So at each point xy, it assigns a vector with these magnitude and direction. So this is the gradient field. Now what I want to do is plot this and see how this relates to what we saw already about level curves and the gradient. Okay, so I'm going to show you a graph of this in a moment, but just let's remember what's happening here. We have a surface, right? Scalar valued function with a 2 input space, 1 output. So it's going to look like again, a surface. And this gradient field is a vector field that tells us the direction of maximal change for this function, right? So if we move to the calc plot. So I'll turn on the surface, what our function looks like, assigning a height to each point x and y. And then I'm gonna shut that off, and I'm gonna turn on our gradient field. So again, this is supposed to tell us kind of the direction of maximal change, so where the curve is steepest, what the direction of steepest change is. And what do we remember about this field for a given surface? That it was the maximal change, and then it was also normal to the level curves. So if I came to this function and created a contour plot, what would we notice about the gradient field, this vector field, and the contours? They're all normal to each one of these curves, right? At every one of these points, wherever you see a gradient vector, it's intersecting the contour lines at a 90-degree angle, okay? So, and again, it's from where it originates. That's the true direction of them. But anyways, this lines up from what we remember about the gradient, right? It's normal to the level curves because it's telling you the steepest place where change is occurring. And so if we throw this back into just the surface, this is a little tough to parse. You can kind of get a sense of it if you take 10 minutes and look around, which we're not going to do. But I will leave this again in the notes for you to play around with. Okay, and at the end of this section, we briefly mention, and we're going to expand on this when we talk about curl and divergence, but the notion of a conservative vector field. And this is really just naming two things that we already know. And one is that, so if some vector field f, let me actually explain like this, that if there exists a function f such that some vector field function is equal to the gradient of f, then we say that big F is a conservative vector field. And that we also say that little f is called the potential function. Now again, you might have some experience with these names from any sort of physics experience. If not, we're going to unpack their mathematical meanings pretty soon as we play more with these. But just to introduce you to the idea, what it means to be conservative, it just means that you are a vector field function such that you're the gradient for some other real valued function. Okay? So that's what makes it conservative. And then what we would call that scalar valued function is the potential. All right. So we're going to leave it there for 16.1 and move into 16.5. And yeah, there are a few exercises in here comparing contour plots and vector field graphs. I recommend playing with the visualizations before tackling these, but it's really not too bad. Nothing too shocking in there. So let's move on to curl and divergence. So we'll start off with curl of a vector field, and then we'll move into divergence. Both are operations on vector fields that look a lot like differentiation, but one ends up producing another vector field, whereas another produces a scalar field. Okay, so first with curl, let's define what this means, and then we'll talk about it more conceptually and intuitively. So if we have that big F as a vector field, assigning a vector to each point. And we know that the partials all exist of P, Q, and R all exist. Okay, so essentially we're playing with nicer functions, or we're avoiding the places where these things don't act nicely. Then the curl is given by, and we write just the word curl of F equals, and then we'll talk about why this is such a crazy formula. But it's the partial of R with respect to Y minus the partial of Q with respect to Z I plus the partial of P with respect to Z minus the partial of R with respect to X J plus the partial of Q with respect to X minus the partial of P with respect to Y K. So this is how we define it. There's obviously easier ways to write this, which I'll get into, but this is actually kind of descriptive in itself of what this thing is. So you think about the I component of the vector field F. Okay, it's given by this P, describes the x directional magnitudes. And so what are these two partials telling us? It's telling me how much my z component, right, my vertical component, differs from my y component with respect to z. So, what is this? This is how much my r is changing with respect to y and how much my y is changing with respect to z. So you can think about it as being the twist, right? If I'm kind of staying fixed on my x position, this might not make a lot of sense, but over time it will. For staying fixed in my x position and I'm measuring here how much z is changing with respect to y minus how much my y is changing with respect to z, that's how much I'm twisting around the x axis. And same here, right? You'll notice none of these partials, here's another way to say it, none of these partials here or here have anything to do with your y direction, right? This is how x relates to z and how z relates to x. And then the last thing over here, same deal. For your z component, your height magnitudes, how much is your y twisting around your x, how much is your x twisting around your y? Okay. So I'm really kind of abusing some words there to get an intuitive notion for curl and where this thing comes from. We're not going to derive it, but just to know that that's what this measures and why we can write this in a nicer way. So another way to view this, first is notationally. I mean, you can use the r sub y, q sub z notation for this, right? P sub z minus r sub x. And this might shine a little bit more light onto what's happening. But what's even more helpful, this is all equal to the curl. What's even more helpful is to think back to the gradient vector for a function of x, y, and z. Right, what did we say this was? We said this was the partial of f with respect to x, and it was a vector. Well, one way you can view this, and this is actually how it's defined, is that this is an operation happening to f, what we call a differential operator. And so f itself is where the operation was applied. So if I take out this f, what I'm really left with is this vector, which is called del. And this vector is a differential operator. It's an operation that can be applied to vector valued functions. Okay, so a function like a vector field that takes values and creates vectors, this can be an operation applied to it, where what are you doing with this operation? Well, you're taking the partials of x, y, and z on each of those components. Okay, so this is a great tool because we can use this in various ways now that we've stripped off the idea of it just being for the gradient. The gradient is obviously still related here, but we have a bit more of an abstract idea. So this is a operation which we can apply, and you can see how it might be tied to what we've been talking about, and we can do it in the following way. We can actually define the curl of a vector field by using the cross product with del. Okay, so we take this operation, we cross it with the vector field f, and what we get from that, if you remember, taking the cross product, it's the determinant of this 3 by 3. And the middle row are these differential operators taking the partial derivatives with respect to each axis. And then P, Q, R. Order obviously matters a great deal here. You're dealing with differences as well as the basis vectors. But you can see, and I'll leave it to you to do so, that when you take this cross product, you should end up with what you see up here. Okay, so there's a couple nice facts about curl that we can talk about, and it relates to being conservative, and then we'll do an example. Okay. So the first fact here is that if we have a scalar valued function and it has continuous second order partial derivatives, then the curl of the gradient of f, again that's a vector, is the zero vector. So this is not so bad to prove, and we're not going to do it. If you wanted to check it out by applying this to any of the simple scalar valued functions we've played with, you'll see that this is the case. And it'd be a good exercise to do that. But the second piece is that if a vector field is conservative, okay, and what does that mean again? That means that it's equal to the gradient of some potential function. Well, if that's the case, if it's the gradient of some potential function, well, then we know that that thing's going to have second order partial derivatives, right? It's going to be differentiable, so then the curl will be 0. So then that tells us that the curl of the vector field is 0, or the 0 vector. Okay, and again, what does it mean to have curl be a vector? What curl really is it's a vector that represents the tendency of, let's say, particles in a fluid to rotate about the axis that points in the direction of curl of f. Okay, so if that vector is 0, then that's not happening, right? But if curl f is a vector pointing in a certain direction, and I can draw this out in a minute, that it's the tendency of those points, or the desire of those points, to kind of go around or rotate around the axis that points in that direction. Okay. So moving on. So if big F is conservative, then the curl is 0. And then the other way around, again, with just a little bit of a caveat, that if big F has continuous first order partials, as long as that's in effect, and that we know that the curl is the 0 vector, then we can say the opposite of number 2, or the reverse of number 2, which is that F is a conservative vector field. Again, why all this fuss about conservative vector fields? Turns out to be a pretty important property of a lot of things that we care about when it comes to work and flux, and it is an important condition for the fundamental theorem of calculus when we scale it up to R3 and Rn. All right, so let me get a diagram going of what we should visualize curl to be. Okay, so briefly, and this is, only really good in R2 cross sections or R3. When you get up to Rn, this notion kind of breaks down. But for now, this is pretty good, which is curl is it's a vector, right? It gives you a vector at a point in the space, and what it does is it points in the direction of the tendency of particles to rotate. So it's at each point, it's a property of the vector field. So like over here, where this red circle is, the question is, if I dropped a tiny horizontal paddle in the water with a little, floaty sticking straight up, the question is, would that paddle in the water spin, or does it have any tendency to spin? So here, the tendency would be very slight, whereas maybe somewhere closer over here, you could see a paddle would want to spin in this water, so that the curl would be a higher magnitude, and you could also get a sense of where it's rotating about and what direction it's rotating about. So that's what the curl vector does. It shows you the axis of rotation, and then the length of it shows you how much the particles here want to spin. Okay, and now let's do an example before we get too far into it, and then we'll talk about divergence. So a thing that we'd be interested in is determining if a vector field is conservative. So let's ask if this, which is defined by x squared y I hat plus x y z j hat minus x squared y squared k hat, is conservative vector field. It's also called path independent, and we'll talk about that in a later section. But just in case you hear that word come up. So to determine if it's conservative, well, we can go back to what we know about these structures, which is that it will be conservative only if the curl is 0. Okay, so what do? We find the curl of this thing, see if it's 0. Then if it is, then it's conservative, and if it's non-zero, then it's not. Okay, so not equal to the 0 vector. So let's go ahead and compute the curl. And again, it's nice to use this cross product algorithm here. And actually, as an exercise, why don't you go ahead and hit pause after we get this set up, and I'll do the same, and then we'll just pick up with the calculation. Okay, so we're back. So I figured out that we hadn't done this with the del operator before, so it probably was good for you to give that a shot, but I'll walk us through this calculation, how it's done. So when we're doing the cross product, right, we normally start with the I component, and we take the determinant of this 2 by 2 here. So we multiply these two and then subtract these two. So when we multiply, we're really taking the operator here. We're taking the derivative with respect to y of this bottom right, and the derivative with respect to z of this bottom left, and then subtracting. So that's why you see this negative 2x squared y, and then minus xy, because this one was differentiated with respect to z. Okay, and then likewise for the j component, except we're doing it with these guys. And remembering that we switch it to subtraction, so when we get the negative difference here, that it'll become positive. And then lastly, for the k component, it's getting kind of busy in here, but working on these, differentiate with respect to x, then with respect to y, and then subtract them, and that's how you get this. Okay, so go through that slowly once to make sure that that makes sense. So this is what we get for the curl of f. And again, if we go back to what we were just talking about, this defines at each point x, y, z, both the axis of rotation, the direction of the axis of rotation, as well as the tendency for those particles around there to want to spin around it. Okay, so it's kind of defining the flow of the air in a room. And here, what we see is that this is not the zero vector, right? So pretty easy to see. This is not the zero vector. Therefore, f is not conservative. All right, so we're going to leave that there. I'll let you do some practice with curl and the del operator, and we're going to use one more application of the del operator. You might be lingering in the back of your head, right? If we know that the cross of del with a vector field is the curl, well, the other vector operation that we know besides, addition and subtraction was what? The dot product. What does this represent? Well, if we think about this intuitively, right, this is the partial with respect to x of p plus the partial of q with respect to y plus the partial of r with respect to z. Again, this is a scalar quantity. So this is a number. And what is this measuring? How much the p component is moving in the x direction, how much the q component is moving in the y direction, how much the r component is moving in the z direction. And so if you think about this, is how much the vector field is moving outward, that's a good sense of what this is really measuring. And again, it's a scalar quantity. This is going to get you some number. And what we call this is the divergence of a vector field. Let me rewrite that. Divergence. So we define div f as an operation on the vector field f, and it's the dot product of del with the vector field. And again, loosely, if you think about this as the flow, or how light particles are coming off of a light bulb, this is a measure or a notion of divergence. So let's just do a quick example here. And this is one that you can do, and again, we'll circle back at the end. So compute div f for this vector field x, y, z. Let's instead do this. X squared yi plus x, y, z, j minus x squared y squared k. All right, so I'll pause it. You give this a shot, knowing just from the definition, and we'll reconvene. So again, if this is your P, Q, and R, then we know that we're taking the partial of each of these here. And so we should get, what, 2xy plus xz plus 0. So we're just left with 2xy plus xz. And again, this makes sense that the divergence would be dependent on what? The coordinates of where you are in the vector field. So you can kind of think of this as the tendency for this kind of outgoingness from that point of the vectors, right? Telling you about fluid or airflow. So one nice, let's see, property or follow up with these two, with divergence and curl, again, telling you kind of these characteristics of a vector field, is that when we compose divergence with curl, it's equal to 0. So what's strange is that, maybe not that strange, but certainly not obvious at the first glance, that the divergence of the curl of f is equal to 0. Okay, so let's work through this in an example. If we look at big F, and that's yz squared I plus xyj plus yzk. You might say, Mally, well, you just handpicked this one. No, that it definitely works for all vector fields as long as they have the continuous second order partials. But let's first compute the curl. So the curl of f, if you go through that here, and I encourage you to do so, right, you'll end up with zi hat plus 2yzj hat plus y minus z squared k hat. And again, it's kind of laborious. That's why I'm punching through that. You've done it a few times, but this ends up being the curl. What is the curl? It's that vector, right? So it's the vector at each point that tells you the tendency to curl. So I want to compute the divergence of this curl vector. Okay, so divergence of curl f is what? The dot product of del with each of the components of the curl vector. So partial y, 2yz, plus partial with respect to z, y minus z squared. And so what do we get? Well, partial of the first is 0. Partial of the second with respect to y is 2z minus 2z equals 0. And again, it's a scalar 0, not the 0 vector. Now, why this is the case, there's no good intuitive reason. There are some good applications in physics when it comes to conservation of charge that show why this would make sense in that context. We might get into that later, but not right now. For now, it's just important to know that when you compose it in this way, when you take the divergence of the curl function, you're going to get 0 as a scalar. So we've covered a lot of ground with these examples and these definitions so far today. So I want you to play with these, and then we'll pick back up next time.